Good day, everyone. Welcome to the second of 4 webinar series here in NoMagic. On September 18th, we had our first webinar about model-based requirements engineering as a new approach for capturing, analyzing, and tracing requirements based on OMG systems modeling language. Today's webinar will cover systems of systems engineering as a set of developing processes, tools, and methods for designing and redesigning complex systems. The session will demonstrate systems definition versus system usage, modeling internal block definition diagrams, using already defined system in the context of another system, modeling SysML 1.4 ports and flows, structural breakdown of a system. The session will be hosted by Dr. Darius Silingas, Head of Modeling Solutions Department at NoMagic. Darius has been working at NoMagic since 1998. He holds PhD in informatics and is OMG certified systems modeling professional, UML professional, and expert in BPM. Darius has built an impressive experience of professional education on systems modeling. He has delivered hundreds of trainings and consulting sessions. If you have any questions during this webinar, you can send them to us using the questions module here. After a presentation, Darius will review all the questions and answer some of them live here. Other questions will be answered later and will be presented together with the video link of this recorded webinars. Okay, Darius, are you ready to begin?
Hi everybody, thanks Eva for the introduction and welcome to the session everybody. So let's start talking about systems of systems engineering, and I would like to start with a short agenda, what we will do today. So we will start by going through just a couple of slides about system of systems engineering concepts. And we will spend most of the time trying to model some example of a ATM system using Cameo Systems Modeler, since I believe that the best way to explain the concepts is by exploring an example. So this should take us some 30-35 minutes, and then we will leave quite a lot of time for questions and answers. So if you have any questions in your mind during this session, please fill them in the questions tab. Okay, so I would like to kick off this session with this cartoon from one of famous books about object-oriented design. So if you think about systems of systems, then in fact I would actually say that any even small thing like ATM is indeed quite a complex structure inside. But as a user, you typically see quite a simple interface how to operate it. While other type of users, for example, administrators or money collectors, would be using different interfaces. And internally, this would be implemented by a number of different parts. There are probably design alternatives how to implement this concept. And we are willing to explore it in a structured way. Otherwise, if we try to understand all the complexity at once, we will be quite frustrated, like this lady in the right hand side part of the picture. So what does engineering process do with modeling? In principle, we actually will be focusing on model-based approach to system of systems engineering. I know that many organizations are using document-based approach, but it is well, we have many issues due to impossible way, impractical ways to tracing and linking different types of information. So to take this as a simplified version of the system engineering process, then we typically start with system requirements and business analysis, and we would be using requirements diagram, use case diagram, or activity diagrams at this stage. And I believe in the first session in this series, you have have seen some of the techniques used here, so we will not discuss requirements during this webinar. Then you go into system analysis and design, or sometimes we call it just high-level architecture. And then you start defining what are the systems and what parts they are composed from. And quite typically, you are using also state diagrams and activity diagrams to show the workflows of some functionalities that are implemented in those systems, and also some life cycle of the system and in which state it can perform what capability. Later on, if you move to detailed design, you typically start adding things like you're still refining block definitions and adding more internal block diagrams, but you are also starting to use typically sequence diagrams and parametric diagrams to explore more detailed, in more details, the interfaces and the responsibilities of the participants, and maybe calculating some parameters based on the relationships of system parts. At some point, you should do evaluation, and then you typically try to link all those things together. So you typically are coming back to linking design elements to requirements elements, and then you also have to integrate the components. So for integration, typically you rely a lot on block definition and internal block diagrams, and sequence diagram is also one of the diagrams which is very often used for showing, demonstrating the scenarios on how the integrated components should work together. And then you do system implementation in any type of implementation technology, which could be, I don't know, some programming language like C, or it could be different techniques on electromechanical system parts. This is a simplified process. Of course, you try to do it incrementally. But what is very important is that we should also do the system architecture at different abstraction levels. So we can try to understand how the system looks from a functional point of view, where we typically just trying to understand the functionalities that system should support, and try to allocate them to the logical parts that should be responsible for for handling these functions. But when you have a logical system architecture, then you can really explore multiple physical implementations using different. For large systems, this is very often that you have to make studies and explore different alternatives and different potential out-of-box components, for example. So at the Magic, what we do, we actually try to promote what we call magic pattern, and magic pattern is kind of recursive pattern, saying that you can actually have multiple levels of architecture, and each lower level of architecture should be traced to the higher one. But I guess the most typical structure is this framework, which has a conceptual architecture, which typically is a basis for deriving user needs. And based on user needs, then the conceptual architecture should support, of course, the user needs. And then based on the user needs, you try to derive more detailed functional requirements. More detailed functional requirements, which then should be satisfied by the functional architecture. Once you have functional architecture, or sometimes people call it logical architecture, then you start making your design choices and design decisions, and then you start to come up with design constraints or even more detailed requirements, which are driven or influenced by design decisions you make. So we want to, of course, allocate functional architecture to conceptual architecture concepts, and physical architecture should also be allocated to the functional architecture. So this is a basic framework, and well, we do actually run quite a lot of trainings on how to do this with SysML. But in a short webinar like this, I think the most productive way of trying to understand these concepts is to try a small case study like ITM with the tool and explain the concepts while we're trying. So I'm switching now to the Cameo Systems Modeler, which is a brand new version of Magic Bureau, basically with SysML plugin and SysML capabilities. And what you see now on the screen is a conceptual architecture of ATM system, and not showing not only ATM but also what are the external systems related to it. I will try to zoom it a little bit so that you can see more elements on the screen. So in this case, what we try to show here is we are just trying to show that we will try to implement ATM, which will interact with customers or cardholders who will try to query the balance or withdraw some cash from the ATM. There will be also some operators which maybe can check the status of ATM and then could maybe give some comments whether to restart it or do something else. Then there will be also support people who will need to load in cash to the ATM, and they also probably will need some information about the status, about how much cash, for example, is left in the ATM. And of course, ITM has to talk to the bank somehow, because the bank will need to update the account information, and basically here we know that transaction concept is typically used, and then we're sending transaction requests, and then we are getting transaction status back to ITM. So this is the conceptual model, which is very simple, and I will just use it as a starting point, but I will try now to create some architecture of ITM system and show you what it means to define a system, and also what it means to use a system which is already defined. So let me start by creating a similar system to the system which is visually shown here in the concept. Well, what I will do first, maybe I will just create a block for the ITM. I will just create a block for the ITM, and then I typically want to refine it and to start showing some of the externally visible interfaces that are supported by ITM. Typically, you do it visually in a diagram, so I will create a diagram. I will create a diagram which is a block definition diagram. So I will do the block definition diagram here, and I will call it ITM black box. I call it black box. Some other people call it specification, and the purpose of this name is that I don't want to be frustrated like was this lady in the picture that I showed in the slides. And I just want to focus on what is visible externally. So I view the system as a black box. I don't see any of the parts, of the internal parts. Let me bring ITM here, and at the moment this is just a block which has no interfaces, and what we can do, we can actually start designing some of the interfaces which ITM has to support. And in SysML, actually, we have a concept which is called a port. A port is some kind of interaction point which is supported by the system, and it provides as an entry point for accessing some functionality that ITM supports. And SysML has two types of ports. You can have the recent version of SysML has two types of ports, and those of you who have used earlier versions of SysML like SysML 1.3, you may have used also other types of ports like like, for example, a flow port, which has been deprecated in SysML 1.4. So in SysML 1.4, there are just two types of ports. One is proxy port, and I will create now just a single proxy port. The easiest way to create it is probably just by selecting the ITM in Cameo Systems Modeler, and then choosing from Smart Manipulator, which is the name for this UI element that's shown here on the right, and just add it to the system. So you see here a label proxy, and then it also gives me some name. So for example, I will say here this is customer operations. So I would like to have a port which provides customer operations here. And this is a proxy port. What it means? It means that this is a virtual thing. It is not anything physical which has, let's say, mass or price or something else. It's just an abstraction which is used to narrow down the functionality that is that should be accessed through this point. So if you think in terms of design patterns, this is actually a facade to the system, which allows accessing only a subset of its functionality. Later on in the physical architecture, we will be using full ports. Full ports are different. Full ports are actually physical things which have some functionality inside, and then they actually can be also defined as types, and they could have their behavior, and they already could have things like mass, like price, and other things. So now I'm doing this at only a functional level, so I typically use only proxy ports at the functional architecture. And now I need to specify what I will be able to do on this proxy port. So in SysML, for proxy ports, you have to define interface blocks, which define the contracts that are supported on this port. So what I will do here, I will say this is customer operations. Customer operations. Maybe I will just give here ITM as well. And then what I will do, I will say I would like to support some requests on this. For modeling requests, I will actually create some signals. So I'm creating an element, a SysML element, which is called signal, which is typically used for modeling a package of information that is being sent. Some people call it message, or some other people call it communication element. The name from the SysML language is signal. So I will say that I would like to be able to start the session. I would like to be able to maybe also end the session. And then I would also like to be able to check balance, and then I would also like to send the signal which is withdraw cache, let's say. Oh, I think so can actually, I think you could have seen that Magic supports spell checking. I omitted D, and then it was marked as a spelling error here. So I'm withdrawing, I'm defining the signal for withdrawing cache. And now what I will do, I will actually say that I would like to create flow properties. Flow properties are things which actually are flowing through the interface block. And then I will use name start, and then I will start. I will basically give it a type start, and I will use. I'm using control space to autocomplete to select from the types that are available in my model. So start session. Then I'm also adding another signal, which is end, and this would be end session again, auto completion. Then I'm using Control and Enter to add another flow property, and this would be the check. Okay, let's call it balance, and I will again autocomplete and use Control Enter to also add the withdrawal. Okay, so I defined a number of signals, and in fact, these, as you can see here, Magic Draw by default checked all of them in out. In fact, all of those will be coming in from the user. So what I will do, I will go and change all of them to in. I could have specified this when I was entering the property here. Let me complete this example, because I will need it to explain the directionality of the ports. So we have 4 signals that are coming in, and then what you have to do, you have to assign the interface block as a type for the defined port. And you can see here the notation is that there is a column and then saying this is ATM customer operations, that's the type for this port. And the directionality is only in because all the flow properties have directionality in. However, we actually will have some of the things going out. For example, on this communication point, we will probably be able to get maybe information about the. I will add another flow property, and in this case, actually, I will try to say it will be an out property. So it will be a property balance info, and I will just say account balance, and then it will be just a number. I will just use real as a type for it. And in this case, I will say it will be out. It will be out. And as you can see now, the notation changed here on the port because it's no longer just in. It's showing the directions, the arrows to both directions. Basically, it is indicating to you that things are flowing in both directions through this interaction point. So that is the concept from SysML 1.4, which is proposed, which is suggested to be used. In fact, I know that some people who are used to using QML are using signal receptions as an alternative to modeling for flow properties. But the preferred way by SysML community is instead of signal receptions to model flow properties here. And let me define yet another port, which I will just define maybe, or maybe I will define it later on. No problem. I will define it later on. So I defined one port, and now I need to understand how this ITM is being used. And if I need to understand how this ITM can be used, then I need to put it in a larger system. I need to put it as a part in the larger system. And also, I would like to come back to the containment tree here and to say that, in fact, I have a little bit of a mess here because I actually defined all things just under the functional architecture. And because you will be using typically different types of modeling elements, you should be grouping them into packages. So I will define a very simple structure. I will say this is ITM package for the ITM definition itself, right? And then I will be creating another package for the interfaces, just because it might be a contract between a couple of systems, and I would like to maybe move them out. So I will move them into interfaces. Okay, but if I look at ITM, it has only one port as a property here, and let me try to define a larger system, and then I will create a package for this larger system, and I will call it banking system. This will be a partial view of the banking system, of course. And what I will do, I can create another block for the banking system, but since my purpose of this modeling exercise is not to explore the banking system, the overall banking system, I will create a specific type of block, which would be a system context. A system context is basically just providing a larger system which is necessary to understand the system that you are working on. And I will call it banking system. And now inside this banking system, I will create internal block diagram. And in this internal block diagram, I will say that I will in fact have ITM as one of the parts of the system. What I will do, I will take ITM definition from here and I will drag it to IBD of the banking system. So what you can see here, it created for me an element which has a particular this port which we have defined, and then this ITM, maybe I will put it to the top here, but it actually has not only the type but also name. So I will tell this this is automated teller machine, and this is a type ITM, and it is an object which is of part ITM, and because this ITM has this port which is defined in the black box, I'm able to use it. So what I will do, I will say there should be another part, and I will add this part from the toolbar now, and then I will say it is a customer. It's a customer. Customer. I will give it the name only, and I will tell that that the customer should be using ITM through this port. And essentially, what I would like to do, I would like to say that that my customer will be sending information about. For example, I can say that it will be calling these functions. So you can drag a signal, and you can say that this information will be flowing through this connector. So start session. It could also be end session. We could also say check balance and withdraw cash. This, by the way, doesn't say anything about the sequence in which this is just saying that this type of information can be sent on this connector. But if we come back to the concept, to the context, we will actually see that customer will do something to the ITM. The ITM will need to talk to the bank as well. We need to talk to the bank as well, and we probably need to bring in bank into this picture as well. And in this case, let me demonstrate the example where I have a predefined system. I have a predefined system, and I will open a new separate project. I will open a separate project which is banking service network, and I will show you how it is defined. So bear with me for a minute or two. It takes a few minutes to load a new project in Magic Draw. So that's how it looks. So I made it a very simple view of this system. I said this is banking service network, and then this banking service network actually has a proxy port, transaction bus, and then it is compliant with the interface block transaction handler. And the inflow property is transaction, whereas the outflow property is transaction status. And you can model also the details what is contained in each of these segments. So this is now defined, but let me now bring in this system into the play at our ITM model. So what I will do now, I will save it, what I've done so far, and I will say in my model that I would like to use an external project which will be then from the banking service network. So I'm bringing it now into my system. You can see, by the way, that it's grayed out because it's only read-only version. It's a read-only version because I'm using a definition of external system which I'm not responsible for. So just imagine this is a agreed standard API for using banking service network. So what I will do now, I will take banking service network, which is definition of this system, and I will bring it in here. So what I have now here, I have a banking service network, and I will just call it banking network. Banking network here, and then I will say that my automated teller machine will actually need to talk to this transaction bus. So I'm connecting it to the banking network object. And as you can see, I'm able to reuse the ports and the types that are actually being defined in the external system. So I'm just using it as a component out of the box to build a larger system, a part of the banking system in my case. So the automated teller machine I defined myself, but the banking network is something external which I cannot modify, but I need to bring it into play for my system to function. So what you will do later on, you can also probably do the following thing. You can actually say now that my automated teller machine doesn't have an interaction point, a port to deal with the banking service network. And here what you could do, you could say, I would like to define a proxy port which would be also transaction handler. Let's say I would like to reach out to transaction handler, and I will connect it to this port. I will connect it to this port, and I will actually assign the type transaction handler to this port. However, if you do this, then I think now I probably have my validation rules turned off. But in principle, I should reverse the type of transaction handler, because here on this port I will have transactions coming in and transaction status going out. Whereas on automated teller machine, I should have the opposite. So what you would do, you would actually say, on the port that it is conjugated. What is conjugated means? It means that the things which are defined in the interface block as in, they will be treated as out, and vice versa. So I'm kind of reversing the interface to reverse the directionality of the flow properties. This is a very typical usage. I could have also defined, as an alternative approach, I could also have defined a separate interface which just redefines this input and output flow properties that are compatible with this other interface. Okay, but coming back to the example that we are doing here, what we have modeled so far, we have seen how to create a larger system and bring in components and see how they are connected. For example, now if I would like to also understand how the ITM will communicate with the banking service network, I can also say that there will be transaction which is coming from handler to the bus, and I can also say that there will be a transaction status which is going out from transaction bus to transaction handler in another direction. You may choose to show it or not show it, in fact, in your case, but becomes a little bit noisy in the diagram here. But in principle, Magic Draw and SysML has capability to display the information flow between the pods. Now, if you would like to decompose the ITM teller machine, further on, what would you do? You would go into the ITM, which at the moment just has those two ports defined. And what would you do? You would say, I would like to create an internal block diagram, and I will call it white box. Other people call it implementation. So black box and white box, or specification and implementation. And now I can see that there are two ports here, and probably you can do some type of design trying to understand how your system will be defined, implemented. And at this one point, what I will say that, okay, I would like to have a ATM controller. So this is the controller, some kind of controller which controls what information is coming in and how you coordinate. And at this moment, I will just connect it to the part because I do not have a type for it and I do not have a port yet. And I will also say that this will be connected to the transaction handler as well. Then later on, what I could also say that in addition to controller, I probably will also need to have another part for the cache manager, some kind of functional object which handles cache withdrawal and maybe also allows to update cache and so on, and it will be connected to the controller. At some point, you can also say that, okay, I will also need to connect another property, which may be something like card security manager. I was tempted to call it card reader, but card reader is more physical architecture concept, and I will just call it security manager. And then maybe we also need to talk to security manager through this, and then talk to the controller. So you will start defining some internal structure of the system, And at this point, I'm showing you only how to define functional architecture. So the concepts are rather functional. But yeah, to continue, I don't have much time, so I will not continue further on. But you could have defined system for the security manager type and the controller and cache manager, and then do the drill down one more level. So it is very typical that people do the following thing, that they come to this view and just assign a hyperlink to the automated teller machine. So if you want to drill down, you would just be going down, seeing how it is further decomposed functioning. But at a certain point, what you need to do, you need to, and I'm switching now to something which is pre-implemented. For example, I will show you how a physical architecture of the ITM could look like. So in this case, what I will do, I will show you a basic structure of the ITM. So we can say that, okay, at the border we will have a display, and we will also have a keypad, and this is a particular design choice, by the way, because especially during in modern times, I think we could also have a touch display, which probably could also handle the entries, right? So we would not need the keyboard there. But typically, you have a display, keyboard, which are both connected to the front panel, and at some point we will need to allocate keyboard and display as allocated elements from the physical architecture that implement the customer operations port in the functional architecture. So here we go more physical, and we can also go in various hierarchical levels. But if we go down in a physical architecture, I think we will be very specific. We will be very specific, and it will be very difficult for a person who is not a specialist in the domain to understand what are the particular physical components that are brought into the play to implement the functional capabilities defined in the functional architecture. Therefore, I have chosen to demonstrate an example on the functional architecture, but exactly the same logic would be also done in the physical architecture. The only difference is that in the physical architecture, you would be using not only proxy ports, but you will also be using heavily the full ports. The full ports, which will be not facades anymore, but adapters or mediators, some objects which do have some functionality and some physical presence here. So that was a quick rush through the basic concepts, how we decompose the systems into multiple abstraction levels and multiple levels of details. Maybe just for the sake of maybe going more into the behavioral side, I would like to also say that, for example, if you want to analyze some scenario of how some functionality, like for example, withdraw cash is being implemented in the banking system, you would need to do behavioral diagrams like sequence diagram, for example. So what you would do, you would go and create a sequence diagram in the context of banking system. What it would do, it would say you have three parts. You have three parts which are objects inside the system, and they and only they can take part in the interaction scenario, which is defined under the system. So I will be bringing all of them into the play here, and just as a simple concept, I will show you. I will show you that I'm sending a signal which is start session right here. Okay, probably this is, I need to start session here, and then I will, the ATM will do something, and then we will then we will be sending another message, which would be withdraw cache, and probably at some point we will need to talk to the bank, and in this case we would be sending a transaction here. So that would be transaction and then this banking network will provide a transaction status here. Just for simplicity, I will ask my diagram to not show the activations, which are those green bars on the lifelines. So what I wanted to say here, that if you want to analyze some behavioral side of this system, you should work with the parts that are defined in that system. And typically people do it recursively at many levels. For example, when you have a start session, something will happen inside automated teller machine. So inside automated teller machine, you will do another sequence diagram if you want to understand it. You would do another sequence diagram and you will say, I would like now to understand how start session is implemented in the ITM. And MagicDraw will tell you that ITM has the following ports, so maybe we would like to bring all those ports, and the cache manager will not take part in the start session, controller will, and security manager will. So you would be bringing in those parts, and you will be trying to model the messages inside. This is very important to not define diagrams like sequence diagrams or, let's say, behavior diagrams somewhere in the blue, out in the blue. You always define these behavioral things inside the context of the system as you understand it now. So let me finish with a demonstration of how you typically do the modeling, and I would like to come back to the slides, and let me see if there are any questions that we have from the attendees. Okay, so one of the questions is if you can obtain a copy of the model. For sure, we will share the models, the copy of the model that I did. We will be able to share it. I think on the webinar website, and then also, in fact, MagicDraw comes with a number of case studies, and I'm not sure which version of the ATM case study is included there, but we also have a more completed version of ITM modeler, which you can get as an example. I always propose that you take a look at examples if you want to. Okay, if you want to understand the concept better. The next question is, how do you model the physical data, like status message, flowing over a physical interface, like serial? Okay, so what you typically do, you define a logical message or logical signal, and then you should have a physical signal of some value type, which basically you would be using in the physical architecture, and you need to allocate things. You need to relate some physical to map some physical signals to the logical signals that you will be using in the logical architecture. So don't intermix logical and physical architecture elements. So I think we probably need an example, but to understand this better. But I'll try to make it for you. But the idea is that in physical architecture, you would be modeling flows of physical things, and you should relate how this physical signal maps to the logical signal defined in the logical architecture. Okay, let me go to the next question. So the next question is the physical. Yeah, I think the next question was just explanation of this, that the physical interface is composed of medium signals, not the actual data. So I'll try to provide an example for that. Okay, there is one more question. Would you recommend a free open source tool for SysML modeling? Yeah, in fact, I'm not that much, let's say, competent to answer that question because I'm not using. I'm using Magictro, which is not open source or free, but based on my knowledge, after discussing with a number of people who tried it, I think the open source solutions are a little bit limited in terms of consistency and ability to integrate. There are some tools which allow you to draw diagrams, SysML diagrams, but they do not allow you to integrate model elements very well. I think that's a well-known limitation that they treat more as a drawing tool rather than modeling tool. And in Cameo Systems Modeler, we really treat model elements as the first-class elements, and then diagrams are just views from a specific viewpoint to understand a specific aspect of the system. So if you want to do a systematic systems or systems engineering, I believe that at this moment at least you want to be able to find the free open source tool which allows you to practice a consistent way of decomposing systems and modeling system interactions at different levels. But I might be wrong, so if somebody has any suggestions for good free modeling tools, just feel free to come back and give us suggestions or discuss in a LinkedIn group. Somebody saying that I'm not wrong, somebody from the participants. Okay, and I think that are all the questions that we have so far. So maybe I have a couple of things to add. We were not able to go much into physical architecture, but I would like to maybe emphasize a couple of practices that people are using in the physical architecture. In logical architecture, functional architecture, you try to focus on the capabilities of the system and try to be independent of the design, physical design decisions or choices. So you're trying to look only at the functional view. And then what happens that when you have to implement it in the physical architecture, you start making choices whether this is a software component, whether this capability is handled by hardware. So you typically end up with a little bit of different, with a slightly different topology of parts, and sometimes these views are very complicated because large systems, even on top level, contain a large number of parts. I have seen systems like missiles, or for example, some automotive machines and medical devices, which then have 20, 30 major components at the top level, and if you try to model connectors and interactions for all of them, it will be a diagram that is impossible to read and understand. So what you would be doing then, you would be using multiple IBDs for the same block, and each IBD would be focusing on a specific aspect, like for example, I know, electricity flow through the system, or maybe some I know, airflow, or you would be looking at a specific scenario. So you could have diagrams which particularly emphasize a specific aspect of the system. Somebody is also asking, Robert is asking, where are the webinars stored? So the webinars are actually stored at the Magic website, but maybe this is a good time for me to hand over the session to Evelina again. because she will be able to maybe show you the website. And also what are the next sessions. So thanks everybody for attention, and I'm pretty sure that this was just the let's say quick ride through the basic concepts, and we were not able to answer all the questions. But if you are willing to explore some of the ideas in more detail, let us know. Send us email, and maybe we can arrange some special sessions with some of you to explore in a smaller, let's say, group and according to your knowledge level, specific aspects of systems engineering. Okay, so I'm handing it over to Evelina, and I will open. I think I will open just the website for the. I will open the website for the. For the webinars, and you will actually see here that you can find the first webinar, which was about the requirements, presented by my colleague Saulius Pavalkis. And there are further seminars that will be in November and in December. Thanks everybody for attention. I'm giving the ball back to Evelina.
Thank you, Darius. And thank you everyone for participating in the webinar today. As Darius already showed to you, we're having 2 more webinars left. Next webinar will be covering the engineering analysis on SysML models. It will be held on November 8th at the same time, 6th, sorry. We are hoping you will actively register and join us. Final webinar of this series will be about defense systems engineering with NAF and SysML, and will be held on December 11th. So again, we hope you will add this date to your calendars and join us in December as well. If there's anything we didn't cover today or you got some more questions, please do not hesitate to contact us. We mentioned before, this webinar is being recorded, so it will take a few days for us to get everything in order, but you will get the link of the recording of this webinar. We appreciate any of your feedback that you would like to share with us, so our webinars would get even better. And thank you again for your time today, and we will be waiting for you to join us in November.